See, all of you see here, there is one more method by which we can show that velocity and centripetal acceleration are always at right angles to each other. Of course, we have seen, but it was a bit tedious kind of knowing. We'll try to know in an easy manner. Okay? See here. If I take velocity as modulus into some angle I cap plus sine of some angle j cap. This is a general velocity vector. Okay? For a particle going along a circle, this is the velocity. What is the speed I have taken here? What is the speed? Speed is v. Theta is the general angle which the speed is making. To draw this in the figure, in terms of figure, you can understand it like this. See. Theta can be any angle, general any angle. Okay. So what I would like to do, if I choose the point P somewhere here, then the velocity vector is like this. This is the velocity vector, and it makes an angle theta with positive x-axis. Okay? It makes theta angle with positive x-axis. So theta goes on changing with time. Is it okay? In fact, theta will go on increasing. As point P comes here, theta will go on increasing from 0 to 360, 360 to 720. But effective angle is always between 0 and 360 degree. Whenever angle crosses 360 degree, assume 360 as 0. As soon as the angle increases beyond 360, make that 360 0 and again start counting from 0. Again, as soon as it reaches 360, again count it from 0. So any angle exceeding 360 can be reduced to a value below 360. So effective angle should always lie between 0 and 360. So by angle, we would mean effective angle, which is always below 360 degree. Okay? Right. So what is the acceleration here? Acceleration will be rate of change of velocity. So v is a constant. Just now we saw derivative of cos theta into I cap plus derivative of sin theta into j cap. Tell me, what is the derivative of cos theta? So one thing you try to understand, this is dt. We have differentiated with respect to time t. So what did I just now taught? Minus. You have to differentiate cos theta with respect to theta. In other words, you have to multiply and divide by d theta. Here also same thing you have to do. You cannot differentiate an expression of theta directly with respect to t. If this is an expression of theta, you have to differentiate with respect to theta. So we have to multiply and divide by d theta. So that means we have to write like this: d of cos theta, very good, by d theta. So we have divided and multiplied by d theta. Same thing here also. D of sin theta by d theta into d theta j cap. So this is known as chain rule of differentiation. It's very important rule. Then, so derivative of cos theta is minus sin theta. D theta by dt is omega. Derivative of sin theta is cos theta. D theta by dt is omega. You can take out omega common. So we have minus sin theta I cap plus cos theta j cap. So this is the centripetal acceleration. The acceleration resulting because of change in only direction. Again and again, since yesterday I have been repeating this. When velocity changes only in direction, we have what is known as centripetal acceleration or radial acceleration. Speed is not changing, so I have kept speed constant. You can see v is constant. Only theta is changing because direction is changing. Now, so what is the method to prove that two vectors are at right angles? A very simple method. Gopichand will tell. You had used in one of the previous questions. Very good, very good. So if you can prove that the dot product is 0, then automatically it gets proved that the two vectors are at right angles to each other. So one is the velocity vector and the other is the centripetal acceleration vector. Centripetal acceleration, I'll put the subscript C. So to show that these two are at right angles. So let us take their dot product. Dot product. So you know how to calculate dot product? When vectors are expressed in terms of I, j and k, multiply the coefficients of I cap, that is x components, then multiply the coefficients of j cap, that is the y components, and multiply the coefficients of k cap, which are the z components, and then add them. Here there is no z component because we are considering a two-dimensional vector, vector in the xy plane. So coefficients of I component, tell me, what is the product? Product. Here it is v cos theta, and here it is minus v omega sin theta. Is it okay? Plus, what is the coefficient of j cap here? V sin theta. What is the coefficient of
V omega cos theta.
V omega cos. You see that both are equal and opposite, you get 0. Is it? V square omega minus cos theta sin theta, V square omega plus cos theta sin theta. 0. So if dot product of two vectors is 0, that clearly implies that vector V is at right angles to vector A. This is the third method by which we saw that they are at right angles. Two methods. Yesterday I taught you one method. Geometrically I showed you that acceleration is perpendicular to velocity by drawing the diagram. Today, around half an hour back, we saw by drawing the angle theta, I explained you. This is the third method by which we are proving that acceleration is perpendicular to velocity. A very fundamental concept, centripetal acceleration is perpendicular to the velocity. Velocity will always be tangential and centripetal acceleration will be perpendicular to that. What is the other name given to centripetal acceleration? Radial acceleration, and or one more name is there. Very good. Normal acceleration. So centripetal acceleration, radial acceleration, normal acceleration, all are same. So normally we use centripetal acceleration and radial acceleration in case of circle. When a body goes along a circle, centripetal means towards center. A circle has a center. Radial means towards radius. A circle has radius. But suppose in general a particle is going along a curvilinear path. Curvilinear path means a curved path. Irregular shape. We don't know the shape. There is no name. There is no irregular shape. Then the general term used is normal acceleration. Normal acceleration. Is it clear? Copy this. Close this. Copy quickly.